Howdy. Okay, so I'm gonna talk to you about the Bergman cyclization mechanism. Bergman cyclization mechanism. Okay, so we start with that ene diene. So here's our ene diene. Oops. There's our ene diene. Okay, and so this Bergman cyclization can actually get started off with heat. Now it's more heat than you're going to have in the body. You can also start it with light. Obviously, there's not a lot of light inside the body. And so that's why they typically started off with an extra dose of electrons reductively at 37. But in the lab, if you want it to happen, um, you actually can in the right system to get it to go into at 37 for certain systems, but for the most part you have to heat it a bit higher than 37 or do something else to it unless you use certain very electron rich systems. So what happens after you do something to kick this off is that once you've crossed an energy barrier or kind of given an electronic push, it's going to do what it wants to do anyways, which is get out of the system. And so this does happen in concerted wise, it seems like. So each of these bonds is going to break. So I'm drawing one bond there. So what's happening is that we're going to get one of these triple bonds is going to break, and each of the electrons is going to go a different way. So the way I have it drawn, it's like looks like two of the triple bonds are breaking, but really it's one triple bond of the triple bond has split up into two electrons, and so that means that there's going to be a double bond that's going to stay, and the two electrons have gone their separate ways. And so we can do the same thing for that other triple bond. And so what's going to happen is that two of those electrons, one from each of those triple bond electrons that broke, are going to go into forming a new single bond. And that other double bond, each of those remaining double bonds, is going to be a double bond plus one electron. Does that make sense? So of each of these triple bonds, so this is a triple bond right here, right? So one bond of the triple bond broke. So there's 3 pi bonds, and one of those bonds broke. Or there's a pi bond and an S bond. So you could say the S-like bond. So that broke. Then there's going to be one electron that's going to go to this carbon. And there's one electron that's going to go to form a new bond. And so out of that, what you're going to get is you're going to get a structure that looks like this. So it has a single bond or two singly occupied orbitals. So those are called SOMOs. So those are singly occupied molecular orbitals that have. So there's 2 radicals. So if I was doing this in the lab, what would happen was each of those two radicals would pull a proton off from somewhere, and I would get a benzene with two R groups on it if I'm doing this in the flask. But if I'm doing this where it's associated with DNA, then what's going to happen is that DNA is hanging around here, and what's going to happen is that this is going to essentially form a bond somehow with DNA. And so it's going to form initially some kind of bond that looks like this, and then downstream it kind of it can vary what happens. But this is how it would look in the first femtoseconds after it encounters this diradical encounters DNA. So this has to happen with it associated with the DNA. What can ultimately end up happening, right, is you're going to get those double strand breaks like we talked about a second ago. But something like this can happen initially. But either way, this diradical is so reactive it needs to be formed close to the DNA. Damn it! Fucking kidding me.